The next model to consider is a single period model. It is used for the products with relatively short selling season or life cycles. Here the classical examples are newspapers, Christmas trees, and so on, for which there is a considerable forecast uncertainty. We do not know how many trees we will sell during the Christmas time, so there is a uncertainty about the demand that we have during the selling season. And because of this short selling season, there is no chance to replenish the inventory. So we will make an inventory, we will make an order for the inventory in the beginning of the selling season. We will get the items then. And then after that, until the end of the selling season, we do not have any chance to make another order and receive another order. We will live with that amount that we have in the beginning of the selling season, during the selling season. And then if it is more than the demand, so we will have some extra units at the end of season, we need to pay this to dispose of them, or we need to sell them at a discounted price. So it is what we call it excess cost. And then if we have less than what will be demanded, so if our quantity in the beginning of the season is less than the demand during the season, so we will have some unmet demand. It is the opportunity cost that we need to pay. And what we want to do in this model is to find a stocking level that strikes the best balance between the expected shortage costs and expected excess costs. We will use this notation. So we have demand denoted by D. This is the stochastic part of our model. We assume that D is uncertain. Then we have Q, which is the order quantity. It is our decision variable. It can also be considered as the production quantity. So we are producing a product that will be sold in a seasonal market, and we do not have any chance to do the production during the selling season. So we can only produce before the selling season and then sell the products during the season. We have selling price denoted by V. This is when the product is sold to the customers in the normal market during the season, in other words. For each of the products that we get, we need to pay variable costs equal to C. It is the, let's say, a purchase cost. Then we have, if we have extra units at the end of the season, we need to dispose of them, and we need to pay U per unit of product, and it is called disposal cost. The other option could be that we sell the extra units at the end of the season at a discounted price equal to S, and it is called salvage value. And we have, of course, some conditions for these different costs, and these are the given values in our model. Now let's calculate expected profit. First, assume that we know demand and it is equal to D. Then we can write the profit as a function of Q, and we will denote it with pi. Here we have different terms in our profit. So first we have revenue, which is V multiplied by minimum of Q and D. Of course, we can only sell the minimum of these two quantities. Then we have purchase cost or total item cost. For each unit of this product, this Q, we will pay cost C. Then if we have extra units at the end, so if we have a non-negative value here, positive value here, then we will pay the cost U per unit to dispose of those extra units. Or Alternatively, we can sell these extra units at a discounted price equal to S. So we have the salvage value here. Or equivalently, we can write profit function as we can see here, like the second line. And based on this, we can calculate the expected profit. So we just need to take expectations of the equation, the first equation that we can see in the slide. Then we'll get this result. So it has two parts. First, in this second equation, we can see two new parameters defined: C shortage and C excess. C shortage is simply V minus C, and C excess is C plus U minus S. These are the shortage cost and excess costs that we have. And then we can say that the first term in this equation on the right hand side of this equation is the expected profit in the case that we have perfect information, and the second term is in fact the cost that we need to incur because we do not have perfect information, and it is the costs for the this is the expected cost for that we need to incur for demand uncertainty. Then we will take the first derivative of the expected profit with respect to Q, put it equal to 0 and solve it for Q to find this condition for the optimality. And what we can see on the right hand side of this equality or this condition is in fact the critical ratio. This is what it's called, critical ratio. And yeah, this is the final equation that we need. We need here to find a Q that satisfies this equation, given that D is a stochastic variable with a known distribution.